Welcome to your lecture, the second lecture, which is again delivered through the flipped classroom mode. You would have gone through the video on the anaerobic digester and also on the RBC, the rotating biological contractor. One of them was an aerobic process, the other was an anaerobic process. Both of them demonstrated the reuse of the wastewater, reuse, recycling, and essentially the amount of water, the water balance which is in the neighborhood is kept as far as possible constant. However, the amount of energy which is required in the entire process is not fully captured in it. However, when the energy used in recycling or reuse of any material, it definitely reduces the overall impact on the environment, which is very important and which is what all our leaders are focusing upon in the recent past. In this lecture, we'll be going through another case study. It's essentially a wastewater treatment facilities tour. You will be again looking at a lot of the facilities or the equipment which is used or processes, unit operations which are there in a wastewater treatment process. However, this particular facility focuses a lot on the recycling and reuse of all the products that go out of it. The other nice thing about this video is, or this presentation is, they show that there's nothing called waste. Everything has a value, and they believe that the work starts when our work ends and when we flush the stuff down the toilet. I will not talk much on this. Let the presentation speak for itself. So sit back and have a useful time of learning.
Located on 85 acres and managed by the City of Santa Rosa's Utilities Department, the Laguna treatment plant services a wide geographical area with over 250,000 residents. Since its inception in 1968, our facility has increased the volume of wastewater it treats from 2 million gallons to currently around 18 million gallons daily. More than 500 miles of underground pipes bring wastewater to the plant, where water goes through 3 stages of treatment within a 24-hour period. The recycled water that leaves the Laguna plant is a high-quality, tertiary treated water that is safe from many reuse options. Okay, so in a moment we're going to head over to primary, our first step of treatment, where solids are settled out. And what we'll find is underneath us are 500 miles of underground pipe converging in 5 major trunk lines at the base of the building over here. Now, as we look around the plant, you'll see many buildings and lots of stuff going on. So it's important to note that it takes a village to clean up water, to treat sewage. We've already seen what's going on for support services and administration and lab. Out here in the plant, we have state licensed operators that run this facility. Behind me is the mechanical services. So we've got the electricians and instrumentation and skilled maintenance, and they're taking care of all the pumps and valves and circuits, etc., that all support the infrastructure of this plant. We're going to head over now and talk about primary and visit our anaerobic digesters. In primary, our first step, we're going to see how solids are settled out and removed. So we want to get the majority of solids removed in this step of treatment. And in a moment, we'll go into the primary building and see long tanks where solids are settling to the bottom, just like they do in the picture of the cone that I showed you back in the lobby. Okay, once we've got the solids on the bottom, a big conveyor is going to push along the bottom of the tank, move all the solids, and pipe them over to these big round buildings. We have 4 anaerobic digesters, each hold 1 million gallons of solids, and this is where solids are broken down. So in this oxygen-free environment, we have certain types of bacteria and archaea, And they don't use oxygen like we do to burn food molecules to make cellular energy. So as they take apart organic material, they exhale CH4, methane gas, instead of carbon dioxide. And we capture that methane, we blend it with natural gas, and we use it to power 1/3 of our energy here at the plant. And that's very substantial because we're an energy-intensive industry. We can get the water clean, but we have to pollute the air to do it. So when we take the methane natural gas and burn that, we're using carbon that's already out there in the atmosphere instead of burning sequestered carbon. And again, we have to burn a lot because water's heavy. It weighs over 8 pounds per gallon, and we're pumping and lifting and moving some 18 million gallons of water on average a day, and that adds up to a huge expense in our PG&E bill, as well as the pollution that goes along with that. So 1/3 reduction from burning our methane and natural gas allows us to be somewhat sustainable. After about a month of anaerobic digestion, where our microorganisms are decreasing our volume, detoxifying the solids for us, they're going to head over to be dewatered and then loaded up into a hopper. And I'm going to keep you in suspense for the moment about what we do with those solids from there, but we'll go over and talk about that in a bit. In the meantime, we'll head on into primary and see what's happening there. This is our primary building, and the sewage is coming in. We're going to detain it for about an hour and a half in these tanks to slowly let solids settle to the bottom. We're pushing solids along by a conveyor belt back down to the end of the tank. On the surface you see the sprayers. They're pushing the floating kind of greasy solids that aren't readily settling down to the end of the tank where they can be periodically skimmed off. Now, as the sewage arrives at the treatment plant, it actually goes through a coarse bar screen to remove the largest items, so any type of rags or paper that come in the sewer can get removed. And then we roll the sewage in an aeration tank to make the grit and the biggest solids settle out quickly, so food from people's garbage disposals, etc., is settled out and removed. That small quantity of material is landfilled, and then everything else comes in these tanks to allow all of the dissolved and floating solids to settle. At the end of the tank here, water is collected at the surface where it's cleanest, and it moves to secondary, and secondary is our next stop. We're standing at secondary now. And in between primary and secondary tanks, we can temporarily detain water. So just out of sight, back here are our flow equalization basins, which allow us to bring a constant flow into these tanks because our system works best when we feed our bacteria a consistent amount of food. During the morning rush, when everybody is using their shower and their sink, that means a pulse of water coming in mid-morning. We can detain water and then bring it back in when we're ready. During those big storm events that we were talking about, where we get storm water into our system, same thing. So once water enters these tanks, you'll notice the water looks really dirty. Well, it is. It's just filthy full of living organisms. So this is where our bacteria, our protists, and our microscopic animals reside, and we're providing them with everything they need to be happy. They've got food, they've got water, and we're bubbling in oxygen. Down in these tanks are diffusers that are blowing air in, so we're providing them with lots of oxygen because, like us, they require oxygen to burn food molecules to make cellular energy. And they're taking apart those carbohydrates and lipids and proteins and nucleic acids, exhaling carbon dioxide to the atmosphere and removing it from the water for us. So we're moving all that organic material. In addition to the carbon cycling through our system, we also have nutrient cycling, and again, that's done by microorganisms. So, you may have detected a faint odor back in primary. That is because one of the smelly byproducts that come from microorganisms is ammonia. And ammonia is created in the sewer as the sewage travels here. Bacteria are already hard at work breaking down nitrogen in organic waste to ammonia or ammonium ion. And that ammonium, NH3 or NH4, is very toxic, smelly stuff. And so these ammonification bacteria have begun a cycle that will continue in these tanks. Once in here, another suite of bacteria are going to convert ammonium to nitrite and then nitrate. So these are nitrifying bacteria. They're taking advantage of all the oxygen that we're providing them, and they are converting ammonium to nitrate, which is NO3. Now, we don't want a lot of nitrate in our water either, because nitrate is a growth stimulant. So it stimulates the explosive growth of aquatic plants and algae in a process called eutrophication, and we don't want that. So the way that we remove the nitrate is in this area you see here. Notice it's not bubbling like this tank is. That is called an anoxic zone. We're not adding oxygen, and in this area of the tank we have bacteria called denitrifying bacteria. They're not reliant on an ambient source of oxygen. They can get theirs right off of the molecule nitrate. They strip the oxygen off, and then N2 gas goes back to its reservoir in the atmosphere. Okay, so that's the nitrogen cycle happening here. Allows us again to take advantage of a natural process and get those organisms to clean the water for us, removing those unwanted pollutants. Now, at the end of about 8 hours in this system, the bacteria have eaten their full, so we have to settle them out. So secondary is really two parts. The first part is, as you see here, allowing microorganisms to do their job, eat up all the unwanted pollutants. And the second part is right around the corner, so we'll head to the clarification basins and we'll see how we settle out and remove bacteria. This is a clarification basin. It's still part of secondary. So water in the aeration basins is going to come over here, all brown and full of microorganisms in the very innermost ring of this basin. It's going to flow out through the trapdoors you see here, and it's going to hit this next ring. Now, that's going to cause the water to stop moving, and then the heaviest material, the microorganisms, are going to start to settle to the bottom. On the bottom, notice there's this big boom arm, and it's got what looks like vacuum nozzles mounted on it. So it's going to sweep around the bottom of the tank, siphoning up all the microorganisms as they settle. The water slips underneath the skirt here and comes up relatively clear on the outside of the tank, where it's captured in the outermost weir and can head off to the tertiary filters. So clarification is a detention time of 4 to 5 hours. And we recycle the bacteria that settle back to the aeration basins. So we have a self-sustaining population. They're hungry and ready to go again. In fact, they're so prolific, a small percentage is culled out and joins the solids in the anaerobic digester. The water then is ready to go on to the tertiary filters. It's collected at the surface where it's cleanest. Now, this particular tank is offline at the moment. So if we don't need treatment capacity, we shut things down to save money, and obviously we need the redundancy, which allows us to rotate everything for maintenance and cleaning. In the meantime, we have operational basins just over here, which we'll go and take a look at and compare. Operates the same way, looks just the same, but this one's full. This clarification basin is operating, and you can see, like we saw over there, the middle is where the water's coming in from the aeration basins. It's very brown and full of microorganisms. As they settle to the bottom, they're removed, and water is coming underneath to this side of the tank, where it's really much clearer, and it's captured in this outermost weir, and this water is now going on to the filters. So our next stop will be to go and check out the tertiary filters. Okay, here we are on the top of our tertiary filter building. We're going to lift the water up to the top of this building, send it across the roof, and then distribute it into each of these tanks you see here. So water enters the tank, where it's evenly distributed across the surface. It's just allowed to overflow its weir and trickle down. And what it's headed for is a 4-foot bed of this anthracite coal. So all the little splices in between the bits of coal are going to act as a fairly fine filter to remove the finest suspended solids, the big clumps of stuff that didn't quite settle in the clarifiers, as well as some potential pathogens. And it's really just minutes to work down through the bed and collect in a filter box at the bottom and then off to disinfection. Now, over the course of about 4 days, the filter gets pretty plugged up and water can't make it through quickly, so it starts to back up. So you see where there's a kind of a dirty bathtub ring. When the water reaches that level, we shut off flow to the tank, we allow the tank to slowly drain, and then we scour the coal bed, clean it, and then it's ready to go again. Once the water travels down through the bed, it's captured in the filter box, heads over to disinfection. Our UV light channels is our next stop. This is our ultraviolet disinfection system. It replaces the conventional chlorine disinfection used in most sewage treatment plants as well as drinking water facilities. And it's really very simple. We have 3 channels set up, and each channel has 9 of these ballast arms. And the ballast arm will be lowered down into the channel, and water will flow in between rows of this ultraviolet light. UV channels have 9 arms per bank and 4 banks per channel. Now, this is a very short wavelength, high energy light that's powerful enough to literally rattle apart and unravel the DNA or RNA of bacteria and viruses. And without DNA, of course, there can be no reproduction, there can be no cellular metabolism, so we have destroyed the organism. And it's literally a 2-second exposure time, that's all that required. So we determine how many channels we run and how many banks within the channel based on our flow at any given time. So from here, the water is disinfected, it's safe for human contact, and it's ready to leave the facility. Finishing our story of sewage treatment at the UV chambers is a little anticlimactic because you can't see how clean the water is. So here we are at our fabulous fountain showcasing the final effluent, the sewage that has been fully treated. A mere 16 hours of treatment time is all it takes to take sewage and turn it into near drinking water quality water. We currently meet state and federal guidelines for drinking water quality. And the reality is that 1 billion people on planet Earth would love to have this water to drink. It exceeds the quality and quantity of water they currently have access to. We ask people as they use water and send us water in the sewer to be conscious of 2 important things. One is water conservation. A drop saved is a drop that we don't have to clean. We don't have to go to the time and expense to clean that water and return it to the environment. And also that some chemicals are difficult to remove in our treatment process, so a discretionary use of cleaning products and personal care products is advisable not only for your own personal health, but for the health of the environment. Our treatment process today is mostly focused on the cleaning of water. Sewage is mostly water, over 99% by volume, but we do have 1% of solid material that we separate out mostly in step 1 in primary. And we're going to find out now what happens to those solids. We left them behind in the anaerobic digesters, where they're being broken down over approximately 30 days and digested. Now we're headed over to our dewatering building and our hopper storage area, and we're going to find out what ultimately happens to those solids and how they leave this facility. All right, here we are at the dewatering building. Solids are going to come from the anaerobic digester after about 30 days digestion. They're going to be dewatered in this building and then loaded into this big hopper you see behind me. This allows us to fill the hopper up and then periodically through the day come in and load it up. So we fill on average 4 of those trailers a day, and the solid material then leaves the facility. Now it used to go 100% to landfill, to the dump. We were throwing away this solid material. But is it really waste? Now, waste implies something has no future value or reuse, and these solids certainly do not fall into that criteria. So the city of Santa Rosa didn't want to put all these solids into the landfill where they don't belong. So they started diverting solids away to a land application program. So we now take solids to agricultural fields where they can be spread and disked in, used just like fertilizer. So you can use chicken manure, you can use steer manure, hey, you can use biosolids. And of course there are restrictions because this is not pathogen-free as it comes through the dewatering. We don't grow human food crops with it. We grow mostly hay. Well, the city wanted to diversify yet again to make even less solids go to the landfill. We now have a state-of-the-art compost facility across the street. So we take these biosolids and blend them with curbside green waste. That's our carbon bulking agent. And we have long beds that are mechanically agitated so the pile is evenly turned. And sensors in the bed wall allow us to continuously monitor temperature and moisture. And over 30 days of active composting, at the end, we allow the temperature to spike up to 150 degrees Fahrenheit for 3 consecutive days, and that removes all pathogens. And we now have what's considered a Class A product, which we can sell bulk on the market for unrestricted use. So you can put it on your fruit trees, your vegetable gardens, your rose bushes, whatever you want. We now take less than 1% of our solids to landfill, and they are almost all reused. So that's a nice direction the city of Santa Rosa has been trying to head, to think about ways of closing the loop. So this facility, this industry, is often referred to as wastewater. Now, I would argue there's no such thing as wastewater, that we have no water to waste. We need every drop of it. And so likewise with the solids, we have to think about reusing these natural resources and not wasting them.
So that was an interesting view which was shared. It is true, we don't have anything to waste. All the things which we have, we are accountable for it. We are accountable to the generation after us also. I hope you enjoyed this presentation where there was a clear demonstration of how we can reuse, recycle, and also recover energy from the material which we term as waste. Material is waste only when it has no energy content. As long as there's energy content, there's life in it. Probably ashes only do not have any energy in it. So till you actually get into the state where it's pure ash, we still have some way by which we can use it. This ash will be the ideal landfill because nothing can grow in it. It's just going to stay inert. So here are the references which were used, and I trust that you found this informative. Thank you for watching. And yes, this is in the flipped classroom mode, and you will be discussing this in the next class, and I'm looking forward to seeing you all. Bye then.